Welcome back to tutorial series. In the previous video, we understood that we'll be solving the differential equations using the Laplace transform method, and we came across a few very important formulas to apply when you solve your problems. Here's the first problem. Solve y double dash plus 4y dash plus 4y is equal to 0 with y of 0 is equal to 0 and y dash of 0 is equal to 3. First, apply Laplace transform. Laplace of y double dash plus 4y dash plus 4y is equal to 4 Laplace transform of 0. Now separating the terms, Laplace transform of y double dash plus 4 Laplace transform of y dash plus 4 Laplace transform of y is equal to 0. Now on applying Laplace transform for derivatives, we obtain s squared Laplace transform of y minus s y of 0 minus y dash of 0 as a Laplace transform for y double dash plus 4 into s Laplace transform of y minus y of 0 for 4 Laplace transform of y dash, and Laplace transform of y is equal to 0. 4 into Laplace transform of y is equal to 0. S square Laplace transform of y minus 3 on applying these conditions plus 4 into s Laplace transform of y plus 4 Laplace transform of y is equal to 0. Now take Laplace transform of y as common and take the other term to the right, which is 3. Now s squared plus 4s plus 4 is equal to into Laplace transform of y is equal to 3. Now s squared plus 4s plus 4 can be written as s plus 2 the whole square Laplace transform of y, which is equal to 3. Laplace transform of y is equal to 3 by s plus 2 the whole square. Now taking inverse Laplace transform of this, you get you can take 3 outside, and this more looks like a shifting property with another property. First, let's try to remove this 2 from inside this thing, so that when you shift this 2 outside, you get e to the power of minus 2x. You have 3 outside, then you will have something of the form 1 by s square. So you can, the inverse Laplace transform of it is x to the power of n minus 1 divided by n minus 1 factorial. So n is 2 here. We obtain the final solution of the differential equation as y is equal to 3x e to the power of minus 2x. Here's the second sample. Find the solution of y double dash plus 4y is equal to 4x that satisfies the initial conditions. Y of 0 is equal to 1 and y dash of 0 is equal to 5. If you observe this if you were to solve using the concepts you learned in the previous module, like variation of parameters method or undetermined coefficients method, we consider this as a non-homogeneous equation and we solve them there. But now we'll see how we'll solve it using Laplace transform. So first, applying Laplace transform of y double dash plus 4y is equal to 4 into Laplace transform of x. Now separating the terms, Laplace transform of y double dash plus 4 into Laplace transform of y is equal to 4 Laplace transform of x. Now finding the Laplace transform of this derivative, s squared Laplace transform of y minus sy of 0 minus y dash of 0 plus 4 into Laplace transform of y is equal to, then the Laplace transform of x is 4 by s square, because Laplace transform of t is 1 by s square. Now taking the terms with Laplace transform of y as common and the others separately, we get s squared plus 4 into Laplace transform of y minus s minus y is equal to 4 by s square. Now taking the other terms towards the right, you get s squared plus 4 into Laplace transform of y is equal to 4 by s squared plus s plus y. Now dividing all these terms using s squared plus 4, you get Laplace transform of y is equal to 4 by s squared into s squared plus 4 plus s into s squared plus 4 plus 5 by s squared plus 4. Now applying partial fractions by taking of the form a by s plus b by s square plus c x plus d by s square plus 4, you will be able to obtain this form. Now you have the other terms too. Now you have 5 minus 1, which will be 4. So y is equal to inverse Laplace transform of 1 by s square plus inverse Laplace transform of 4 by s square plus 4 plus inverse Laplace transform of s by s square plus 4. Now you can see that 1 by s square, the inverse Laplace transform of 1 by s square is x. Here you need 2, this is of the form 2 by s square plus 2 square can be written as sine 2x. So you have 1 2 extra which will come outside. So you can write this term as 2 into sine 2x. So this can be written as cos 2x. So this is your solution for the given differential equation using Laplace transform. Here's an application-based question. An alternating EMF E sin omega t is applied to an inductance L and a capacitance C in series. Show by transform method the current in circuit is E omega divided by P square minus omega square into L into cos omega t minus cos pt, where P is given by 1 by LC. Now, since based on the derivation we saw using Kirchhoff's law in the third module, they have mentioned that we have inductance and capacitance, but we don't have resistance. So that term of r dq by dt becomes 0. So applying the other terms, L d square q by dt square plus q by c is equal to E sin omega t. Now Laplace L into di by dt plus q by c is equal to E sin omega t. Now taking Laplace, you get L di by dt plus 1 by c Laplace transform of q is equal to E into Laplace transform of sin omega t. Now you know that for differentiation or I dash, Laplace transform will be L into Laplace transform of I minus I of 0 plus 1 by c into Laplace transform of q, which is equal to E into Laplace transform of sin omega t can be written as omega by s square plus omega square. Now it is Laplace transform of on applying that initial condition or initial current is 0, L into S Laplace transform of I plus 1 by c Laplace transform of q, which is equal to E into omega by s square plus omega square. Here we are finding it for I instead of q because they've asked us to find the current and not charge. So in this step, instead of continuing with charge, you're continuing with current. Now you have Laplace transform of I and Laplace transform of q, which is not necessary here. You want this in terms of I again. For that, you know that I is given by dq by dt. So applying Laplace on both the sides, you get that s into Laplace transform of q minus q of 0. So initially we are considering that charge is also 0. So Laplace transform of q is given by 1 by s Laplace transform of I, which you will be substituting in this place. On substituting, we obtain this form. So now you take Laplace of transform of I common and you have Ls plus 1 by Cs inside, which is equal to E omega by s square plus omega square. Now on taking L by S as common, you have s square plus 1 by Lc inside, which is equal to E omega by s square plus omega square. Now they have given that 1 by Lc can be written as P. You can write the terms. So you have E omega s, where you take s here divided by L into s square plus omega square into s square plus p square, where p square is 1 by Lc. Now you have E omega by L into p square minus omega square into s by s square plus omega square minus s divided by s square plus p square. As mentioned, you have p square as 1 by Lc, and you get this step when you apply partial fraction to this system. So when you take inverse, you apply partial fraction because you cannot take inverse for such a term. So you divide it to take inverse Laplace transform. So when you take inverse all these are constants, so you take them out. So when you take inverse Laplace transform for this, you obtain I is equal to E omega by L into p square plus minus omega square. This is inductance into cos omega t minus cos pt as a solution or the current of the given differential equation. You have a few practice problems here and the solutions too. To practice them to get a better clarity and a hands-on practice with solving differential equations using Laplace transform method. Thank you.